Okay, let's dive into this. Welcome, everyone, to today's Explainer. We're going to be unpacking a really fantastic Grade 7 mathematics chapter, and it's called Finding Common Ground. If you've ever wondered how numbers connect behind the scenes, or if you're just someone who loves a good puzzle, well, you're absolutely in the right place. We're going to break down exactly what this chapter is trying to teach us. And trust me on this, it's a whole lot more engaging than just staring at a chalkboard and memorizing a bunch of formulas. We're talking real-world problem solving, a bit of mathematical detective work, and even some mind-bendingly huge numbers. So let's get started.
Here's a quick look at our agenda for today. First up, real-world math dilemmas. 2, defining HCF and LCM. 3, conjectures and counterexamples. 4, the magic of primes. And finally, number 5, puzzles and mystery colors.
All right, moving right into section 1, real-world dilemmas. Because math isn't just numbers on a page, it actually starts with real-world problems. And this brilliantly illustrates exactly what I mean. Take a look at Samiksha's dilemma. She has this room, 12 feet by 16 feet, and she wants to cover the entire floor with square tiles. But she has some strict requirements. The tiles all need to be the exact same size, the length of each tile has to be a whole number of feet, and she wants to use the fewest tiles possible, to save time, effort, and her knees. So the big question is, how do we figure out the exact size of the square tile she actually needs to buy? To solve this, we just have to break it down step by step. For the tiles to fit perfectly across that 12-foot breadth, the side of the tile has to be a factor of 12. Looking at step 1, we see those factors are 1, 2, 3, 4, 6, and 12. But wait, the tiles also have to fit perfectly along the 16-foot length, which means the side also has to be a factor of 16. Step 2 shows us those factors, 1, 2, 4, 8, and 16. Okay, so look at step 3. What are the common factors here? The numbers that show up in both lists are 1, 2, and 4. This means Samiksha could use 1-foot tiles, 2-foot tiles, or 4-foot tiles, and any of those would fit perfectly without her needing to cut a single one. But here's a question for you. Can you explain why she should use the largest tile? Well, remember her original goal. She wants to use as few tiles as possible, right? So naturally, the larger the tile, the fewer she actually has to lay down. Boom! The 4-foot tile is the absolute perfect solution.
Now let's look at another real-world scenario. On the left, we've got a sweet shop that gives away free gajik. If you haven't had it, it's this delicious sweet made from sesame seeds and jaggery, and they give it away every 7 days. On the right, we have a customer named Kabamai, and she visits the shop every 10 days. So we have these two sequences running side by side. The shop gives out free sweets on days 7, 14, 21, and so on. Kabamai visits on days 10, 20, 30. You get the idea. So look at those lists and ask yourself, when will Kabamai eat free sweets again? Basically, we're looking for the exact day those two totally separate schedules finally align. If you trace down both lists, the very first number they both share is 70. On the 70th day, the schedules sync up perfectly and she gets her free gajuk.
Okay, moving into section 2, defining HCF and LCM. This is where we take the intuition we just built and formalize our findings. So the crucial point is, we intuitively just applied two really fundamental mathematical concepts. The first one is the highest common factor, or HCF. Formally, it's simply the highest or greatest of the common factors of two or more numbers. By the way, you might also hear this called the greatest common divisor, or GCD. Now think back to Samiksha's 12 by 16-foot room for a second. The highest number that divided perfectly into both 12 and 16 was 4. That 4-foot square tile was literally the physical representation of a highest common factor. And then there's the other side of the coin, the lowest common multiple, or LCM. The definition here is the lowest or smallest of the common multiples of two or more given numbers. Again, map this directly back to our sweet shop problem. We have the multiples of 7 for the free sweets and the multiples of 10 for Kabama's Stizits. The lowest common multiple between 7 and 10? Yep, it was 70. That 70-day wait was exactly the LCM in action. It's pretty cool when you see it applied like that. Which brings us to section 3, conjectures and counterexamples. This is all about thinking like a math pro. Now that we've got the calculations down, how do mathematicians actually explore the unknown? Let's read this definition straight from the text. Statements or claims made without proof or verification are called conjectures. You see, mathematics isn't just about finding an answer. It's really about looking at data, spotting a pattern, and then making a general claim about how the universe of numbers actually works. But of course, a claim is just a guess until you actually verify it.
Now, what's really interesting about this slide is how mathematicians actually disprove these conjectures. The key question is, can you find a counterexample where the conjecture is false? In math, you definitely can't just assert a conjecture is true just because it works a few times. But to absolutely disprove a conjecture, you literally only need to find a single instance where it breaks down. Just one single example where the rule fails. That's what we call a counterexample. It is an absolutely vital tool for mathematical reasoning, teaching us to always critically test our assumptions.
All right, let's shift gears a bit for section 4, the magic of primes.
Check out this absolutely massive number. 41,024,320. Now, let me be clear, this is not the largest prime number itself. Actually, scratch that, it's wilder than that. This massive figure represents the total number of digits in the largest prime number discovered as of October 12, 2024. I mean, just think about that for a second. A number over 41 million digits long, and it's only perfectly divisible by 1 and itself. If you actually tried to write that out by hand, you'd run out of ink, paper, and probably your sanity. It truly highlights the infinite, awe-inspiring scale of what mathematicians are studying out there.
And finally, section 5, puzzles and mystery colors. Let's move to and see how this builds into some really fun applications of the math we've learned.
So now we get to take all these concepts of multiples and factors and apply them in a way that's actually fun. The chapter outlines this brilliant interactive activity called the Idli-Vada game. Here's how it works. You choose two numbers, right? Let's say 2 and 3. As you count up, whenever you hit a multiple of the first number, you call out idli. So for 2, you'd say idli on 2, 4, 8, and so on. When you hit a multiple of the second number, 3 in this case, you call out vada. So 3, 9, 15. You get it. But the real magic happens when you hit a common multiple. When you get to 6, which is a multiple of both 2 and 3, you have to shout idli vada. It's a fast-paced, totally entertaining way to train your brain to instantly recognize lowest common multiples.
Which brings us right to our final puzzle, this really beautiful visual straight from the text. This grid shows the numbers 1 through 100. But if you look closely, notice that every single number has a different, specific colored circle design around it. Some are solids, some are split into halves or thirds, and the colors change. I promise you, these aren't just random decorations. They represent deep mathematical patterns based on factors, multiples, and primes, which is exactly what we've been unpacking today. So I want to leave you with this provocative thought as we wrap up. Look closely at this grid. Based on everything you now know about finding common ground, can you decode the hidden mathematical patterns in these mystery colors from 1 to 100? Thank you so much for exploring with me today, and keep looking for those patterns.